thank you for tuning in. This is chapter 2 of Stochastics. Today we are going to learn more about probabilities and how to find them. Most of us use the term probability or chance quite intuitively. We all know expressions like 50-50, and that one is usually used when there are two opposing outcomes, but very rarely when they are of equal probability. With some everyday objects, we believe that we know how they behave. So, for example, a coin when tossed is believed to land on either side with the same probability, namely 50%. With a six-sided die, we naturally assume that every side will occur in roughly 1 out of 6 rolls. We are going to find a probability empirically. That is to say, we are going to conduct our very own experiment. Due to time constraints, we will only be able to arrive at an approximation, but the concept will become clear. So we are going to use our trusted D6. And because it's the highest number that we can roll, and because it often plays a special role in certain die games or board games, we're gonna aim for 6s. So the die is 6-sided. Let's show some naivety and roll it 6 times. See what happens. That's not a 6. That isn't either. Not a 6. Totally not a 6. Trust me, that was no 6. 1 to go. Whoops. Well, it would very obviously be wrong to assume from our results that this die cannot roll 6s. It just didn't feel like it. So we are going to need many more rolls so that lucky streaks, or, well, streaks of bad luck, just do not carry as much weight as when we only do very few rolls. Let's do 100 rolls and see where that gets us. which basically means we are going to write down either 6 whenever we roll a 6 or 6 dash, the complementary event, which stands for all the other outcomes. We are not going to note down 1, 2, 3, 4, and 5. They all are summarized by 6 dash. We are going to spice up our raw data table with a few more numbers. We are going to note the number of rolls that we have done so far. In the column headed A, we are going to note just how many 6s we have rolled so far. This is called the absolute frequency. But the absolute frequency is of very little value. If you roll 5 6s, but you rolled 1,000 times, well, that's not a lot of 6s. So we are going to add a third number called the relative frequency. And that one is going to be a fraction. We are going to divide the number of 6s, the absolute frequency, by the number of rolls. And for convenience's sake, I am going to use 5 dice to make it a bit faster, to expedite the process. That's a nice word. Alright, let's get rolling. No 6s at all. This means we have done 5 rolls. We have an absolute frequency of 0 or naught. And a relative yield some fractions. We are going to use them in a second step once we've got our data and start visualizing that. But for now, talk about bad luck. If all goes well, we have now showed off what bad luck means, and maybe we can catch up a bit. Actually roll a couple sixes and actually start rolling better. Oh well, here we go. You're gonna have to trust me on that one. It did roll 6. For some reason, this makes me happy. I like patterns. But a couple more 6s would also be quite welcome. yet so far the relative frequency has been below 1/6. It would be great if the dice would roll in a way that we could get above 1/6 for a couple entries. Doesn't seem like it. On to the last column. If I were playing a board game where I needed to roll sixes, chances are I would be grinding my teeth into a very fine white powder by now. And the powder into dust. Come on, one last six. There it is. So there we are. We've had really bad luck at times. We did not have any proper lucky streaks. But well, that's chance for you. That's random. And that is one of the reasons why you can't just do 6 rolls or 10 or 20. And let's face it, 100 are not enough either. Now in the classroom, that's an easy problem to solve. Get 25 students, have each of them do 40 rolls, and already you have way larger numbers. Large numbers will play a role next when we take our data, visualize it, and see where we can take it from there. Now with the law of large numbers. Let's take a look at a visualization of our data. We're going to put the relative frequency on the vertical or y-axis. Steps of 0.01. So every little box is going to be 0.01 as frequency. On the horizontal or x-axis, we are going to put the number of rolls in groups of 5, or in increments of 5. This will be our first stop at 20. And we're going to label 40, 60, 80 and 100 to make it a bit easier on us. The fractions that we noted down earlier, I have converted them into rounded numbers, and I rounded to the second digit. For one, I cannot draw accurately to the third digit anyway. On top of that, our numbers were far from optimal, but with only 100 rolls, that was to be expected. For the first 15 rolls, we had no 6s at all. I forgot to label that axis. So up until 15 rolls, the frequency was 0, naught, nada. It then went up continuously for quite a while. First to 0.05, then to 0.08. Then it pretty much skyrocketed for a while, and after that very little happened. So at 40 rolls we were at 0.13. We then went down a bit, up again, there. Up once more, down once more. We are now at 75 rolls. We went up again to 0.15. And after that, we hit a streak of pretty bad luck. And we ended up with a relative frequency of 0.12. That's a bit removed from the frequency we would have hoped for, 0.16 or 0.17, close to 1/6. So let's connect the lines just because we can. It says the law of large numbers. 100 in this context does not count as a large number. If we were to do this for an extended period of time, and like I've probably said before, have your 25 students, have every one of them do 40 rolls, 50 rolls, 100, and you will get what we could call better numbers. You would get more reliable numbers, because all these small streaks of either bad or good luck will eventually even out. So anytime you do this, you will get slightly different graphs at the beginning. But if you were to do this for really large numbers, they would eventually get really close to the red line, and they would not leave it again. So let's take a look at, well, the law of large numbers. What does it say? Given a large number, well, that's hardly surprising. A large number of what? Of samples. In our case, a large number of rolls. What happens? The relative frequency of an event changes. Our event was rolling a 6, and this frequency, the more often you do it, it converges. That is to say, it stabilizes. It stops jumping about as it does in the beginning, and it really stops moving that much, and it converges to the true value. And of course, it cannot be expected of you every time you do any kind of experiment is either taken from somebody else's work, from literature, or from, well, let's call it common sense. And that is how we arrive at probability for every elementary event, for every outcome. We assign a number. And that is where the sample space comes in again. We're going to do that. Everyone will eventually do that for every event that can be found in the sample space. And that number is called the probability of said event. So, which number do we use? Of course, we cannot just make that number up. We're going to use the number that the relative frequency converges on. Once we've done lots and lots of rows, once we have a large number of samples, so this is what it all boils down to. If you want to find the probability for anything, you're in for it. Spending a lot of time doing repetitions over and over again. Or, well, you use numbers found in literature, numbers that you would expect. So, for example, for our die, we're going to put a capital P for probability. We're going to put the event in parentheses. And we're going to say that is equal to 1/6. And there's basically two ways of saying that. You can say P of 6. Is equal to 1/6. Or instead of saying P, you can call it the probability. that's the probability of the event 6. So, this is going to be a bit abstract, maybe for completeness sake. Stay with me. Picking up where we just left off with P, which gave us a way to note down probability. What is the general situation when we are talking about a probability distribution? We have a random experiment. And we know the sample space. Now, in our example, the sample space contained the possible roles from 1 through 6. Because this definition is going to be a bit more abstract, a bit more general, we are going to label the outcomes with a lowercase e, and we're going to number them. And you can think of that number just like a house number, for example. So we've got event number 1, we've got event number 2, and just exactly how many events there are, we're gonna leave that open. Still, the last event needs a house number, needs to be properly addressed, and very irritatingly for many people who start mathematics this way, we're going to label it with a letter. And that letter is going to be a natural number. Natural numbers are 1, 2, 3, 4, 5, 6, 7, and so on. So there are no negative numbers in here, there are no fractions. It's really just as if you were counting them. What do we expect of that letter P that gave us the probability? Well, it's got to take an outcome, an elementary event from the sample space, and it's got to turn that into a number that we can treat as probability. That number is going to be a real number, meaning we have digits after the point. So a function from the sample space into the real numbers. And it's going to assign exactly one real number. To each elementary event from the sample space. function this letter P, which enabled us to write P of 6 equals 1 over 6. This is called a probability distribution. If it satisfies two conditions. Condition number 1. And this is even more annoying for those people who hate doing mathematics with letters. The probability of any outcome needs to be equal to or larger than 0. So we are going to allow a probability of 0 for impossible outcomes. But we want positive probabilities for the rest. Doesn't make sense to have negative probabilities. So what about this letter I? The idea is that I takes on all the house numbers, all the values that we need. All the way from the first one to the last one. For every single elementary event that is possible or impossible, we need P to give us a number that is either 0 or larger. And there is a beautiful shorthand for all of that. I'm going to put it in here because I think it's just fantastic. You can ignore it for the time being. I'll probably make a video eventually sometime in the future just for these shorthand notations. And there's a capital letter A turned on its head, which means for every, which must be a bit confusing, and it corresponds wonderfully with German für alle, but it just doesn't do that in English. So I hope that this notation is actually used in English. I'm gonna have to check on that. And the idea is we're gonna say I is somewhere between 1 and n. So for all the values of I that are between 1 and n, that has to be true. The second and last condition. If we add up the probabilities for every single elementary event, so P of E1 plus P of E2 all the way to P of En, we want these to add up to exactly 1. The idea being that if we do an experiment, the probability that any one of the possible outcomes will actually happen needs to be 100%. We cannot have any leftovers here. space consists of 6 outcomes, the numbers 1 through 6. Now, does our P fulfill the first condition? We are going to assign a probability of 1 over 6, 1/6, to the outcome 1. And we are going to assign that same probability to every other number. This obviously satisfies, checks condition number 1. All probabilities are 0 or higher. And we have of course deviated quite a bit from the results that we got earlier. This is now an ideal die or a fair die, and we kind of expected to roll every number with the same probability. Chances are it is physically impossible or extremely hard to actually manufacture such a die. So this is a theoretical value, but it's what we are going to be using. Condition 1 met. Now condition 2 is of course very easily verified. I mean, it's 6 times 1 over 6, come on. So, like I said before, if or when we roll a die, we expect to have a 100% chance of it rolling a number from 1 through 6. It will not stand on an edge or stand on a corner and not give us a number. And that is the end of this chapter. Looking forward in chapter 3, we are going to take our sample spaces, our random experiments, and our newfound probabilities, and we are going to work with them on a couple of simple introductory experiments, but they'll be experiments that happen in several stages. So we're going to look at things like what happens if you toss a coin repeatedly, or for example in a board game, what happens if you get to roll a die 3 times in a row. How is that written down?